Oh, yeah, thanks, yeah. Thanks, yeah, that's good.
Thank you. Okay, we look forward to our second talk by Professor Ramote from Queen's University in Canada. He will talk about Dirichlet series and the conjecture of Erdős.
Thank you. Thank you very much. I just remembered that Kalyan and Srini, I knew them since they were graduate students. And in fact, if memory serves correctly, I was in the same apartment complex, not the same room, apartment complex as Kalyan Chakraborty was when he was a graduate student. We all had to suffer through the same cook that was making breakfast for us, who was always half drunk. That was in Besant Nagar. That was way back in 1984, I think. And I think I knew you when you were a graduate student at TIFR as well, because I stopped by TIFR. And so our memories go back a long way. Now, I wanted to call this talk on a conjecture of Erdős just for the fun of it. But I think you all know that Erdős made thousands and thousands of conjectures, so that wouldn't be very informative. So I thought I'd add something by saying Dirichlet series with periodic coefficients and a conjecture of Erdős, and that would probably pin it down to only one conjecture. So hopefully that will be, is this the thing that we need to use to go down, up and down? Yeah, okay, I got it, yeah, thank you. So Dirichlet series with periodic coefficients. So what are they? So if you have a natural number n, and if you have a periodic function with period n, we can associate to this periodic function a Dirichlet series, LSF equals summation f of n over n vs. And we can write this Dirichlet series, because it only depends on the residue class modulo n, we can write this as a linear combination of Hurwitz zeta functions. Zeta s a over n. So Hurwitz zeta function is that, in case you didn't know. It's an extension of the Riemann zeta function. When x equals 1, it is the Riemann zeta function. But if x is not equal to 1, it could be these other functions. Now, the theory of Hurwitz zeta functions was well studied by Hurwitz, and he showed that these L functions admit an analytic continuation to the entire complex plane, satisfy a complex functional equation like the Riemann zeta function. We can inject that information into this expression here. We can inject the theory of the Hurwitz zeta function in here, and then deduce that LSF has an analytic continuation for the entire complex plane with a simple pole at s equals 1 equal to this particular sum. In other words, if summation f of a is 0, it has no pole. Particularly if it's residue 0, LSF extends to an entire function. So if L1F exists, it can be written as a linear combination of digamma function, and I'm going to talk about that. So since the time of Dirichlet in 1837, these series have occupied a central place in number theory. For example, the celebrated theorem of Dirichlet that there are infinitely many primes in any co-prime residue class hinges on the fact that L1 chi is not 0. So the non-vanishing of these L functions, L1 chi in particular, is crucial for arithmetic theorems. And in our case, we're going to be trying to investigate the non-vanishing of L1F. So what is this conjecture of Erdős? In 1965, Erdős, in a written communication to A. Livingston, made the following conjecture, that if you took an arithmetic function which only takes plus or minus 1 or 0, then the L function attached to that should be non-vanishing. Okay. So if n is even, the conjecture is trivially true by parity considerations because of the residue has to be non-zero, so we have to focus on n odd. In other words, the case n even is trivial and can be dismissed, and the difficult case is when n is odd. Now, if n is odd and congruent to 3, this was a consequence of a general theorem that I proved with Sarada in 2007. And there we were extending earlier work of Baker, Birch, and Wersing, who applied the theory of linear forms and logarithms to study this problem. And it turns out in that case, when n is congruent to 3 mod 4, some sort of minor amount of algebraic number theory attached to cyclotomic number fields can be used to dismiss that. So that was dismissed way back when, 2007. And since then, I have been thinking about, other people have been thinking about the case n congruent to 1 mod 4, and finally, after 15 years or thereabouts, we made a breakthrough thanks to my two collaborators, Abhishek Bharadwaj and Siddhi Pathak, who are not here as far as I can tell. Abhishek Bharadwaj is a postdoctoral fellow in CMI, and Siddhi Pathak is now faculty at CMI. So they are in Chennai, but they're not here. In fact, Siddhi, I think, is giving lectures in that ATM school in CMI as we speak. So these are the two people. And the theorem we proved is that if capital N is not a perfect square, and you have a function with period n which only takes odd values, then L1F is not zero. So in other words, we had to generalize the Erdős conjecture. The Erdős conjecture was plus or minus 1 only as values, but we now extend the range of values to odd values, and it turns out this generalized version is in substance easier to prove than the original Erdős one. It's one of these counterintuitive things. Somehow the generalization of the problem is easier to solve than the original, simply because we have an induction argument, and this odd business makes the induction argument go through smoothly. So in other words, conjecture 1.1 at the top is true whenever n is not an odd perfect square. This means that the case that capital N is a perfect square is still open. So there's still some more mystery surrounding this problem that we have not penetrated yet. So the last theorem here, our particular methodology that was used in this paper shows that if n is an odd square, there is sadly an arithmetical function which takes odd values in which L1F is equal to 0. So our method just simply does not extend to this case. All right, so what are our methods that we have injected into this thing? So we thought that firstly, functions of Dirichlet type seem to make an appearance. What are these functions? They are periodic functions, period n, and they're supported only on coprime residue classes. So those are called functions of Dirichlet type. Such functions can be written, of course, as a linear combination of Dirichlet characters. So you can write G as summation G chi chi, and then we can now partition the summation over the characters according to the conductor. The conductor will have to divide n, so D divides n, and then the inner sum is the contribution coming from characters of conductor D. Just like in the last talk, we saw a distinction made between old forms and new forms, and somehow this kind of distinguishing had to be there. This is the new one of the new ingredients that has to be introduced here. You have to understand where the L function is coming from. Is it coming from some old part and new part? What was making it difficult was exactly that phenomenon. So here, dn dg is the component of G arising from characters of conductor D. And so in this context, we say a function is imprimitive if there is no contribution at all from characters of conductor n. There's no contribution whatsoever. It's imprimitive. So in other words, G chi 0, that inner product is 0 for all primitive characters chi mod n. So that's an imprimitive Dirichlet type function. So we start off with the easy case, let P be a prime and G be a Dirichlet type arithmetic function. If G is imprimitive mod P, then we can tell what it looks like. It has to look like a multiplicative of the trivial character. So we just, that's the proof. It's a one-line proof. I'm not going to go through it, but it's more or less simple. So we begin with the base case of a prime. And in that case, we can characterize these functions precisely. So now, Abhishek had already studied in his PhD thesis this aspect of how the primitive and imprimitive functions kind of penetrate into this problem. And he showed that if G is rational valued, period n, L1G is 0, then G chi 0 n, which is a primitive character, is actually an imprimitive character. In other words, if I have an Erdős function or any function which has imprimitive components, then it has at least one primitive character in its character decomposition, it has to, L1G has to be non-zero. So we can now focus on these lower level things that are actually contributing to them. So this was the big idea that we needed to first understand. We needed to separate where the L1F was coming from, and it was coming from lower levels. This was not there in the Baker-Birch-Versing approach. So this would settle some cases of Erdős conjecture, but clearly not all. On the other hand, in the famous theorem of Baker-Birch-Versing that I've been alluding to, if G is of Dirichlet type and rational valued, then L1G 0 implies G is identically 0. So they settled if G is of Dirichlet type and rational valued, finished. But now we need to allow, remember, our function is not a function of Dirichlet type. It's only, it takes plus or minus 1, and it's not, it may not be supported only on the coparameter, it may be other things as well. So that's another part of the problem, so we have to deal with that. In the Erdős conjecture, we do not have a function of Dirichlet type. However, we can write our L function as sums of L functions attached to functions of Dirichlet type, as will be shown on the next slide. So here's Baker, Birch, and Versing, and I think Baker and Versing sadly passed away. I think Birch is very much alive. Here in this picture, I think you can see he just finished explaining his famous conjecture, the Birch-Swinnerton-Dyer conjecture. Okay. So what is our idea in trying to, because I just talked about functions of Dirichlet type, and I told you Erdős functions are not of Dirichlet type. So how do you go back and forth? Well, the idea is that you could take a series, you could take your Dirichlet series, and you could partition. Now, before in the previous slide, I partitioned functions of Dirichlet type. I wrote it as sums of Dirichlet characters and partitioned it according to the conductor. In this decomposition, what you do is you take the divisors of n and then partition the sum according to the GCD, and then now you can pull out a d to the s out of this, and then L as GD. This GD is now a function of Dirichlet type. Now, this decomposition, along with some basic character theory, allows us to derive a new criterion for the vanishing of L1G, and I call this the Bharadwaj criterion because essentially it appears in Abhishek's thesis, the Bharadwaj criterion. So what is that? Well, it relies on an orthogonality principle. It is important to study the vector space spanned by the values. So there's another new ingredient now from the Baker-Birch-Versing approach. You need to study what kind of vector space is spanned by the special values. And now, for those of you who know cyclotomic theory, you know that L1F is actually a linear combination of essentially cyclotomic units. So this is an important idea. So we will decompose this vector space as a direct sum of orthogonal subspaces. And the W sub D of n is the subspace of L1Fs, with F being Dirichlet type and F being supported only on characters of conductor D. So that's the vector space. And then we can prove a little lemma, which is very cute, that WD of n is actually WD of D. You can kind of go back to the level and shrink it down. And then another important idea is that this the sum of the WEs is a direct sum. So what's going on for some of the, there are at least half a dozen experts in the room, so let me just say this out loud. What's going on is by decomposing this L function value, we're able to say which cyclotomic field is contributing what to the final result. So the proof of this fact actually uses Baker-Birch-Worsing in a fundamental way, so we need to do that. So this now allows us to say, if you take your function g, which I wrote in the previous slide, of Dirichlet type, then the Dirichlet type function has, so in the previous slide, notice what, let me just point this out, notice that, not this one, notice that any periodic function can be written as 1 over ds with L as GD with GD of Dirichlet type. GD is now of Dirichlet type. So now we have reduced the problem to studying only functions of Dirichlet type. Now we go to this next slide, and we now see in this particular, decompose the function as functions of, decompose the Dirichlet function type function as functions of these type, where this is a contribution coming from the conductor D, and it turns out, and I'm just going to flash this technical criterion, the vanishing, there's a new vanishing criterion. What basically it boils down to for the half a dozen experts is that if L1G vanishes, L1, that script D, N, D, G also vanishes. Each of those components has to vanish because of that direct sum orthogonality decomposition. So this is the new vanishing criterion. So each of these things has to vanish. For every proper divisor, you get this, and you get another thing. And by the way, for some of you who know about what's called the Okada criterion, you can deduce the Okada criterion from this. Yeah. So when we apply this, we apply it systematically. First, we take a function which is of period n, such that LSG is entire, and given by this particular shape. Then L1G is 0 unless G is identically 0. Forget the proof. An application of the vanishing criterion now leads to G being identically 0. So basically, using the vanishing criterion, you can now prove this particular theorem. And now let's try and prove the main theorem of Erdős by contradiction. So suppose that we have a counterexample to Erdős conjecture. And that's why, by the way, I had to generalize the problem to odd values instead of just plus or minus 1 business. Odd values because when we do the induction, the function is going to change, but the parity is preserved. So that way, this is so this is an interesting thing, isn't it? I mean, this happens in mathematics all the time. It's the induction hypothesis. What is the induction hypothesis? Sometimes if you have the wrong induction hypothesis, it doesn't click. You have to have the right hypothesis. So here, this is the one that we have to take. Because it's too technical, let me just say the essential idea is that if you have a function of period, if you have a counterexample, then you can see that we're going to recursively construct another periodic function depending on with same period, such that L1G is 0. And the Dirichlet series will be of this type. LSG is this type. So in other words, starting from a counterexample, we'll construct another function g such that LSG looks like this. And then from the previous slide, we find that if L1F is 0, L1G is 0, and that forces the Cn over P and the Cn's to be 0, and then finally it means that you have a contradiction. So basically, now look, the method by which we crush the function f to get a function g is facilitated by another function, capital J we call it, which has certain special properties that are essential to the argument. So let me just tell you what the idea is. This from the imprimitivity of the thing, we have to go to the vanishing, and in his thesis, Abhishek had shown that if G is rational valued and periodic, then G chi naught n is imprimitive. I already alluded to that fact earlier. And then using this capital J function, we kind of peel off parts of the function until we're reduced to the prime case. And then finally the prime case has been dealt with, and then the problem is solved. That's basically the idea of the proof. Okay, so this magic function J is a little technical to write, but more or less it can be given explicitly in this fashion. And it turns out this function is always 0, so you can peel off. But it has a nice property that it can be made to agree with the values. So essentially what's happening is you have your L function written as a linear combination of logs of cyclotomic units, and you're kind of peeling off this contribution from higher fields until you get to the prime level. And these functions Hn of g, maybe I won't go in too much in detail, but given an integer function g of period n, you've produced this other function script Hn, which agrees with g on the co-parameterized classes modulo n. At the same time, its associated L function vanishes. So in this way, we keep changing the function, but the L1g of that new function that we keep changing is still 0. So nothing has happened to the L1 value, but we're changing the function slowly until we reduce it to the prime level case, keeping in mind that the Erdős conjecture is known when G has a primitive character component. So finally, that's what we do. So systematically, we keep the function will agree with the same function, but this function vanishes. And so we'll use the previous setup to peel away at our function to enable a certain inductive process, eventually reducing our problem to the case of prime. And in this context, we had to not quite look at z-valued functions, but z of 1 over n valued. And thank goodness n is odd, so it still works in our favor. So this is the final theorem that finally you get this reduction, and so these inductive functions still satisfy the thing to make the reduction possible. With these recursive sequence of functions in place, we can now complete the proof because of those 3 properties that were outlined in the previous slide. You quickly peel off the function and reduce the number of prime factors in an inductive manner. So this is, in case people want these slides, or the paper for that matter, I'm happy to provide it. So this is the final step. Okay. So further applications of the method resolves the Erdős conjecture whenever the modulus n is not a perfect square. In particular, if n is square free, the conjecture is now true. Note also the Murthy-Sarada result that I talked about is included in this thing, so we get that too. You don't need to resort to the other method. And as a corollary, the point is I think am I able to write on this thing? The Hurwitz zeta function So here, psi of x is the digamma function. So in other words, the constant term in the Hurwitz zeta function is the logarithmic derivative of the gamma function. And because we just finished evaluating L1f can be written as a linear combination of digamma values. So in other words, one of the consequences of the Erdős conjecture is that there is no relation of the digamma function with plus or minus 1s as a coefficient. And in fact, from our theorem, there is no relation with only odd numbers as coefficients for all the things, right? So that's the interplay between primitive and imprimitive characters is what complicates the explicit construction of a fundamental system of units, like the Ramachandra units in cyclotomic field. So for those of you who know some cyclotomic theory, you know it was a big problem, open problem for a long time until the 1960s when Ramachandra constructed an explicit fundamental system of units for the cyclotomic field, and had to do with this primitivity, imprimitivity, this lower level, higher level, same idea as old forms, new forms, this problem. Where is the thing coming from? So same difficulties arise in the study of circular units, and Bass's theorem, which classifies all the relations that you can have amongst the circular units. There's a famous theorem of Bass that tells you what are the possible relations that you can have amongst the circular units, and Bass made a conjecture. It was not quite right, but it was almost right, and it was corrected later by Enola. So there may be further applications to understand distributional relations. So this is what I would like to. I think I have 5 more minutes, or go. 6 more minutes. Oh, 6 more. Okay, good. So what is interesting in this particular derivation is the presence of what can be called distributional relations. The digamma function satisfies a distributional relation. So do the Bernoulli numbers, Bernoulli polynomials rather, satisfy. So there's a kind of commonality, and in cyclotomic units also have a distributional relation. So there's a kind of a distributional relations theme that's kind of underlying these kind of problems, and there may be a larger theory which I think we just put our finger on, but it's youngsters in the room who are looking for good PhD thesis topics certainly can look at this distributional relations among circular units, among digamma function, among Bernoulli polynomials, and a host of other functions that exist in nature that keep on appearing again and again. And that's also complicated by lower levels and higher levels. So this kind of idea that seems to be same as this problem. So I just thought that I would highlight this particular, there's Kalyan, I think, and there's Srini. This is the 20 years, everybody was 20 years younger. It's a 70th birthday conference in 2003, Bangalore. And so I think most of you can recognize yourselves here. Some younger people, you know, floating around. Adhikari here, you know, Balu, and I think our honorary citizen of India, Professor Walter. Okay, well, thank you very much for your attention. Happy birthday, Kalyan and Srini.
Thank you very much for the nice talk. Are there any questions?
Oh, this Krishna Arjun has a question.
Hi. So in your first few slides, you said that if some average of f of a is vanishing, then you don't have a pole. And then, yeah. So do you have a formula for the value of L1 in something along the lines of average of f, something along the lines of function like that?
Yeah. The value of L1 will always be a linear combination of the digamma function.
Okay.
And the digamma function has some sort of asymptotic expansion that you could use, and it will give you some idea. But does that answer your question, or was that?
So I was hoping if you have an explicit formula, let's say L1 chi is non-zero, of course, but L1G is equal to something which is explicitly you can construct from G. But it seems you cannot get rid of the digamma function, which is...
Oh, but we have formulas for the digamma function. That's the point. The digamma function is a linear form of logarithms. So you can always express L1G, L1F, when F is periodic, always as linear forms and logarithms of cyclotomic units. That's
Okay.
Yeah.
Okay.
So that just like in the classical case.
Okay.
Just like L1 chi, you can do this. Yeah.
Okay.
Okay, thank you. Any further questions? Yeah, yes, there.
Mathematical question.
Of course.
Yes, the picture you showed of the Wirsing was taken in Oberwolfach in the late 70s when we were playing non-kinetic duet with recorders.
Okay, well, thank you. Were you there in that picture? Were you also there?
In Oberwolfach, the one you showed.
Okay, yeah. Oh, yeah. All right. Yeah. So thank you for that, yeah.
Okay. Are there further questions or comments? That does not seem to be the case. Yeah, then let's thank the speaker again. Thank you. And yeah.
Oh,
We also have a little gift
oh,
for you.
thank you. Oh, we should, is anyone taking a picture? Okay. Thank you. Is it a mug? It's a mug? Yeah. I better turn this off.
Good, there's a break of half an hour now. Right? Yeah.